You're welcome once again to this tutorial. And today's tutorial, we are going to focus on double sideband suppressed carrier demodulator. So basically, as we do normally after modulation, there should be a demodulation. And in my previous tutorial, we talked about how we can generate a Dsbsc modulated signal by using a balance modulator. And now we also talked a little bit about the ring modulator, of which we were saying that the diodes had been arranged in a circular form, hence it named ring modulator. But basically, since we have been able to understand how we can modulate an AM wave using AM Dsbsc wave, we are going to learn about how to modulate this signal. So let's kick it off. Ds, let's say Dsbsc, refers to us extracting the message signal from a Dsbsc wave. So basically, double sideband suppressed carrier is like extracting the original information or the message signal from the double sideband suppressed carrier wave. So basically, if you use the method of maybe balance modulator to kind of come up with a resultant modulated wave, at the end of the day, you need to demodulate the wave to get the original message back when it gets to its original destination or the desired destination. So basically, when you use this method, or when you get such Dsbsc wave, you need to use a Dsbsc modulator to extract the original information. The fact is that when you do this Dsbsc modulator, you don't expect to go and use maybe square law demodulator to demodulate it, because the square law modulator was used to modulate the one with both the carrier frequency being part of it. And when you see over here we suppress the carrier, and therefore we need to talk about its demodulator aspect. So looking at it, it has two main types of which you will be able to demodulate a Dsbsc signal. The first one is the coherent detector, and then the second one is the Costas loop, and we are going to talk about them one after the other. Now let's look at the coherent detector. The coherent detector, we use a local oscillator to basically produce our carrier frequency wave, and we assume that we have the modulated signal S of t. So let's look at the coherent detector. For this one, as I was saying, assuming that we have our modulated Dsbsc signal, which is equal to S of t. That's S of t is the Dsbsc signal wave. And then we need our carrier wave as usual, C of t. So in doing that, we pass it through our modulator, and then from there, we'll be able to get our output. Remember that the Dsbsc wave was achieved by using a product modulator, because during the general equation discussion for Dsbsc, we multiplied the message signal by the carrier signal, and we were able to achieve our X of t for the Dsbsc wave. So when we want to do a demodulation for it, we also need a product modulator in order to extract it. So let's see what we can do in order to extract our original message signal. So we're looking at it, the same carrier signal which was used during modulation of the Dsbsc signal is being used again to detect the message signal, and that process is what we call the coherent detection. So basically, this is the block diagram for it. We have the product modulator. So I will say the product modulator to be called PM. So PM equal to product modulator. So you have your input signal, which is our modulated Dsbsc signal. Okay, this one will be passing through a product modulator, and remember that we are using our carrier signal as well, C of t, which is equal to AC cos omega ct. Now the output of the product modulator will be passing through a low pass filter, LPF. We are passing it through a low pass filter because our message signal that we want to extract is of a lower frequency, and therefore it will allow the low pass filter will allow the lower frequency signal to pass whilst attenuating any other frequencies. As a result, we'll be able to get our V out, which is our demodulated signal. So this is generally the block diagram for a Dsbsc demodulation. So in short, I will say that if we want to extract the message signal, we will do this by multiplying our modulated wave or Dsbsc modulated wave by its carrier frequency wave. And by multiplying them, we'll be able to get an output, and that output needs to be passed through a low pass filter. After passing it through a low pass filter, the resulting signal is of a lower frequency, and the output is our message signal. So, not to waste much time, let's do a bit of mathematical analysis for it. Now, from our previous calculations that we have done, or mathematical analysis that we have done, we know that our x of t is equal to a cos 2 pi fct multiplied by m of t. That is our modulated signal. Because when we did the calculation here, you saw that we are having m of t here and then cos omega ct. That is the same thing that I've written over here. Or you can rewrite it as AC m of t cos omega ct. They are the same thing. This is my modulated Dsbsc wave. Now, you're also aware that our carrier signal C of t is equal to AC cos omega ct. Mostly, they add the phase to it. That one, it's not something that I want to consider, because at the end of the day, I'm going to say that maybe the phase is either 0 degrees or 90 degrees and other stuffs. But if you like, you can include it as well. So in getting my message signal will be my carrier signal will be C of t equal to AC cos omega ct. Now, the output of the modulator, it's V out equal to x of t multiplied by C of t. This is the relationship that exists between the input and the output of the modulator. And therefore, my V out is equal to AC cos omega ct multiplied by AC cos omega ct. You can decide to ignore the phase and move on. Now, this is what I have. In multiplying it, we are going to get something like A squared AC squared cos omega ct cos omega ct. And we all remember that during one of my tutorials, cos omega ct cos omega ct was equal to 1 over 2 into bracket 1 plus cos 2 omega ct. And in expanding it, we are going to get A squared c over 2 multiplied by 1 plus cos 2 omega ct. Remember that this one, there was let's say here there was a m of t here. I didn't include it, so we need to include it here. M of t here should be m of t, and then from there we will multiply everything by what? M of t, because m of t is multiplying by it. At the end of the day, we are going to get m of t multiplied by A squared c over 2 plus m of t multiplied by over 2 cos 2 omega ct. Now, this is what I have. So what I can do is that, looking at this one, I'm done with passing it through the product modulator, PM. Now, the output of the PM is supposed to be passed through a low-pass filter. When I pass the output through a low-pass filter, I'm going to get my original message. This is the output. When I pass it through a low-pass filter, because this one contains a higher frequency, which is the carrier frequency, this low-pass filter is going to attenuate it, and therefore this one will go to 0. Now, my output of the low-pass filter is going to give me AC squared over 2 m of t. And you can see that the amplitude of this message signal is we have a scalar version of it. Looking at this stage, if you want to eliminate this DC value, you can pass the resultant output of the filter in a multiplier, and the multiplier must have a gain. The multiplier must have a gain of 2 over AC squared, and therefore it will help us remove the DC gain, leaving the final one to be what? M of t. So, in summary, for the Dsbsc demodulator, using the coherent detector, we pass the information, the modulated wave, which is x of t, into a product modulator. That modulator, the modulator's output will be passed through a low-pass filter, which will help us eliminate any unwanted frequencies. From there, if we want to eliminate the DC gain, we can pass it through a multiplier. And the multiplier must have a gain opposite of, or the reciprocal of that of the gain of the output of the filter. And therefore, per that one is going to give us 2 over AC squared. The resultant output is going to give us M of t. This is how you'll be able to do a demodulation for a Dsbsc signal. For the number 2, which is the Costas loop, I'm not going to derive much more about that, but I'm going to talk a little bit about it. This one also follows the same principle. We use the same carrier signal that we use in generating the Dsbsc signal, and that's being used to detect the message signal that we want to extract. So that is not actually okay. So for the Costas loop, it's used to make both the carrier signal and then the locally generated signals in phase. So following in the block diagram, you can actually check it out. But basically, I'm not going to talk much about the Costas loop. So if you need much information about the Costas loop, just hit me up in the comment section and I'll get you some resources that you can read more about the Costas loop. And to talk briefly about it, it consists of 2 product modulators with common like input signal, which is S of t, and then S of t is the DSB modulated wave. We make use of a voltage control oscillator for that, and it should be out of phase of minus 90 degrees phase shift to one of the product modulator. So basically, if you want to know much about it, please hit me up and then I'll give you resources to read about. So thank you for watching and see you in my next tutorial.